but thanks again, and sorry about this. So my name is Roberto Perdisci. I'm a professor at the University of Georgia, where I direct the Institute for Cybersecurity and Privacy. I'm also affiliated officially with the Georgia Tech, where I'm an adjunct professor there in the School of Computer Science. And the work that I will present today is, in fact, a very close collaboration with Georgia Tech. And well, I guess about me, in terms of my research, is mostly oriented towards network and web security, and so today, the talk will be oriented towards network security. And the talk is about IoT Finder, which is a system that we built a couple of years back funded by DARPA, and this is for efficient large-scale identification of IoT devices via passive DNS traffic analysis, which I'll explain what that means for the ones of you who might not have that type of background on network security side. And with that, I guess, Gabriela, I would go ahead. All right. So first of all, let me try to clarify what do I mean with Internet of Things. So of course you can find many definitions of this term. I don't think there is any clear definition, to be honest. Things are really fuzzy, right? But let's try to give one, right? IoT describes physical devices that run software, right, and that connect and exchange data with other devices and systems over the internet or other communications networks, typically, well, wireless in many cases, but not only. Now, what does that mean? Because this could include anything pretty much. And the way I see it and the context, the scope of the work that I'm going to present considers IoT devices as basically devices that are built for a specific purpose or function, right? So for example, think about a light bulb, right, has a specific function. And like a smart speaker has a specific limited set of tasks that it can accomplish. This is unlike general purpose devices, right? Computing devices such as laptops and desktops, but also smartphones, right? Because you can install a variety of apps on these devices. You can do anything pretty much that you would want to do with a computing device. And again, IoT in contrast are limited in the scope of the functionalities that they essentially implement and they're designed for. So again, this is fuzzy, right? You can think of a smart TV actually getting closer and closer to a general purpose computing device to some extent, where you can install many apps and you can browse and so on and so forth. So again, there is a fuzzy line, but for the purpose of this talk, we're going to focus on things such as, light bulbs and cameras and smart speakers, vacuum cleaners that connect to the internet, and so on and so forth. I hope this makes sense. So, um, apologize for my voice. It's a little bit. I had a little bit of a cold recently. So IoT devices have been growing in terms of numbers, right? And the number, especially of devices that are directly connected to the internet, they've been growing really fast throughout the past few years, and they're expected to grow almost exponentially in numbers as we move forward. And unfortunately, one thing that is clear at this point is that there are strong market forces that determine the fact that many of these devices are not secure. What I mean with that is that the priorities for the designers and developers of these IoT devices is time to market and functionality, right? Security comes way at the bottom of the priorities. And obviously, as you can imagine, because of the sheer number of these devices on the internet, this can become a huge issue, and I will talk about that. So what are the problems, the security problems that we most commonly find in IoT devices? Well, things such as authentication. Many devices, especially the cheapest ones, may come with hard-coded or guessable password. passwords, which means that others can log into our devices and potentially, there are privacy violations. We are exposed to privacy violations like eavesdropping and so on. Um, but also, because of the software development life cycle for these devices, there is a lack of automated security updates, and often the network services that are exposed to the internet that run on these devices are vulnerable to remote attacks. And also, there are issues related to use of insecure communication protocols, right? Whereby IoT devices that transfer potentially sensitive data like video and audio over the internet, they might use insecure protocols, for example, weak or no encryption, which means that the confidentiality of the information that we transfer, I mean, the devices ship over the internet to, say, a cloud endpoint can be compromised. Next slide. So, so let's see, what are the threats, right, that these potentially vulnerable IoT devices pose to the internet in general? And one thing that is clear, it's been shown there are many instances, actually, really world examples of this, is that IoT devices can be compromised and used to create large botnets. So what is a botnet? A botnet is, so bot stands for robot, a device that can be controlled remotely, and net for network, of course. So a network of these bots are compromised devices that can be remotely controlled by an attacker. And the consequences of these is that if an attacker is able to enlist an army of compromised IoT devices, although these IoT devices are resource constrained, they can actually generate large amounts of network traffic. Next slide. And so what that means is that this enables attackers to potentially launch attacks against other entities on the internet. For example, a cloud server somewhere that provides a sensitive or either even safety-related service. And this can obviously have real world consequences, right? So these are type of attacks listed here are denial of service attacks, distributed denial of service attacks, whereby again these compromised devices are used to generate high volumes of traffic against a particular victim to basically take it offline. And again, if this victim is offering a sensitive or particularly valuable service, that's going to be a problem economically and potentially in other ways as well. Next slide. And this is not hypothetical at all. In fact, I mean, there are many examples of attacks here. I'm reporting just a couple, but many examples of attacks, of cases in which denial of service attacks have been used for cyber warfare as well as for political reasons. And these attacks are frequent. They happen on a daily basis with variable amounts of number of attacks as well as volume of attacks in terms of the volume of traffic that is generated by compromised devices around the internet. And then technically speaking, they use a variety of ways in which the traffic is generated to cause these issues of availability issues for important services. Next. So that's one type of threat that is well documented. But there are other types of threats that we don't often think about that are exposed by, or caused by vulnerable IoT devices. So one of them is the issue of lateral movement for stealthy APTs. So let me parse this sentence for the ones of you who are don't work in this area. APT means advanced persistent threats. So these are typically sophisticated, well, relatively sophisticated attacks, depending on what target we are talking about, against enterprise and government and military networks. And so here the scenario is one in which there is an attacker, right, on the internet, potentially a nation state that wants to accomplish cyber espionage, right, to a military or government network. Say that this attacker is able to perform an initial compromise, right? So there is a machine inside the enterprise network that is exposed to the internet somehow, right, and is reachable and can be compromised. And once this machine is compromised, one of the things that the attacker often wants to do is to be as stealthy as possible and stay within this now compromised network for as long as possible without being detected, and also move around, meaning compromise other machines and take control of other machines on this network to try to find data that is of value for intelligence purposes, for example, right? Again, say an espionage case. And so in this case, basically what we talk about is lateral movement when the attacker starts from an initial compromised machine and then compromise the second one and then a third one, again, looking for valuable data that can be exfiltrated. Um, and the reason why we call them APTs is for the P is persistent. Persistent because the attacker wants to make sure to stay in that network as long as possible because new data will be generated, right? The attacker wants to exfiltrate, continuously exfiltrate data for, again, potentially cyber espionage type of cases. Now, as you can imagine, if a machine such as a server or a laptop or a desktop computer is compromised, it's easier, I mean, it's hard, but easier than other cases to at least try to do an analysis, right, of what happens on that machine. For example, you can run anomaly detection system or even the old school type of antivirus software, right, to scan the machine for compromises, for malware, for malicious software. And so, it potentially is it is possible, right, to eventually detect that the machine was compromised, and then, of course, action needs to be taken to remediate that machine. However, imagine that an attacker, after the initial compromise, scans the internal network slowly, so not to be detected easily, and scans the network to specifically try to identify if there are any IoT devices within that network, and then uh, moves laterally to these IoT devices. So meaning that it implants malicious software in the IoT devices themselves. Now, why is this important? Because nobody's going to scan a fire alarm with antivirus software. You cannot install antivirus software in the smoke alarm. In fact, you cannot install pretty much any software unless you really break into the device, right? You actually exploit it. And so this allows the attacker to hide, and which means that even if all the other machines like laptops and desktops and servers that have been compromised are remediated, the attacker is still inside the network and at any time can restart the infection from inside. So even if the access from a remote entity is blocked, maybe because the initial vulnerability is found and remediated, well, the attacker is already inside. So it can always try to start again propagating, moving laterally from the hideout, the IoT devices that were compromised to other machines. So hopefully this gives you an idea of the not only of the attacks that are already documented, but also attacks that are possible and that are caused by the presence of these devices in an enterprise or a home network also. Next slide. Okay, so now let's talk a little bit about going to the specifics of how a device can be compromised. So often, or let me put it this way, the easiest way to reach or compromise an IoT device remotely is if that device is directly accessible, right, somehow. Meaning that from the internet, you can reach out to that device through a network communication, right, and send specifically crafted network traffic that will exploit some vulnerability in that device. This is very common. There are many devices on the internet that are actually exposed. Cameras are a very common example, but there are many others, and you would be surprised by the number of devices that people put on the internet and are publicly reachable, and they don't even realize. I mean, the owner of the device doesn't even realize it, right? Um, Now, one may think, well, the ones of you who maybe have more of a network security background might think, well, in my house, all my IoT devices are behind a NAT. So a NAT is, well, let's say, think of it for the ones of you who don't have necessarily a security background or networking background. Think of your access point, your Wi-Fi access point. What that access point does is really create sort of like a wall between the public internet and your home network, whereby data can easily go out, but coming in, of course, I mean, if you have requested data, then the data you request, you can get it, but your devices cannot be easily reachable directly from outside, meaning that an attacker may not be able to initiate a connection directly to one of your devices. So there's this type of firewall functionality that comes with the access point. It's a natural thing in a way, and actually comes from, it's sort of like a byproduct of IP IPv4 IP addressing exhaustion, really. But let's not go into that. The point I think that to take from here is that you might think that your devices are secure, but again, they might not be. Next. And in fact, like we said earlier, well, because we have a mix of devices in our networks, right, including our laptops and phones and so on. Well, you might install an app that seems legitimate on your phone, like a game, that when you bring it home, right, I mean, when you are in your home network, that game could scan your local network and then try to compromise one of your IoT devices. You don't even know, like you have no idea whatsoever that your phone continues to run normally. Your IoT device, in fact, continues to run normally. But if the device is compromised and it's a sensitive device, like a camera, for example, of course, you have a lot of privacy issues and whatnot. So the fact that your devices are behind a NAT are not a defense. It's a little bit more difficult, of course, for an attacker to penetrate in that case, but it's definitely not impossible at all. In fact, malicious apps on phones are actually quite common. Next. So hopefully this gives you kind of a background of why is it important to study IoT security, right? The security of these little IoT devices that nowadays many of us have in the network. And sometimes we don't even know how many we have, how many are connected to the internet, right? It's quite amazing. Um, so our goal was to try to study this problem, which is quite challenging, of determining, okay, so given a large network, are there any IoT devices in this network, and of what make and model, right? What is the vendor? What is the model of these IoT devices? So we want to essentially enumerate these IoT devices. So why do we care to do it large scale? Well, think of it this way. So let's take an ISP network. So let's say Comcast or Cox Communications or AT&T and so on and so forth. They have millions and millions of clients, right? Many of them are home network clients, but they also have enterprise network clients, including sometimes sensitive networks like government networks. They act as the upstream providers, upstream traffic providers for our connectivity towards the internet for these sensitive networks. So now the ISP may want to kind of determine or have an assessment of the health of the ISP network overall, right? And as a way to say, okay, so if I can enumerate IoT devices that are vulnerable in my client's networks, I can inform my clients and tell them, hey, you need to take care of these devices, and essentially have this awareness of the fact that your ISP network is potentially supporting this, or you know uh, yeah, so this potentially offering connectivity to vulnerable IoT devices that may be used for different attacks like we saw earlier. And so in a way, solving this problem would be sort of like a step towards, having global awareness, and potentially reducing global internet risks due to compromised IoT devices. Now, there are multiple ways of doing this. One may think that, well, the ISP network can simply scan their clients, right, and probe, send network probes, and see how the machines respond, and then classify the machines based on these responses. There have been many methods proposed in terms of active probing of devices to determine their models, basically. I mean, what they are. But unfortunately, like we said earlier, many of the client networks within an ISP, a large ISP, are NATed, meaning that they have that wall in between the ISP and the internal parts of the network. So this is not typically something that is easily doable, unless you have an agent inside each network, which has privacy implications and so on. So ISPs typically don't want to do that. So the question was, all right, actively it's difficult, maybe not possible, given privacy implications. Can we do it passively? And so the interesting thing is that, of course, the ISP can see all the traffic that its clients are sending and receiving from to and from the internet. And so the idea was, okay, is there a lightweight way of monitoring this traffic so that we can then try to identify, by just looking at the traffic coming out of a local network, if there are IoT devices in it and of what kind? And the approach that we took was to monitor DNS traffic. So DNS stands for the domain name system, which I will describe briefly in the next few slides to give a little bit of background. But for now, let's say we can monitor this particular type of traffic. And the idea is, again, the goal is really to detect IoT devices, including if they are behind NATs, uh, and also independently of whether these devices or the client networks are assigned IPv4 or IPv6 addresses. And this is a detail, so don't worry if you cannot follow this. There are some implications related to IPv6 as a protocol and IP addresses because of just the sheer number of possible IP addresses that or the size of the IP address space for IPv6 that makes things a bit more complicated when you do active probing. But again, this is a detail, so we can probably move forward. If you have any questions, I would be happy to answer at the end. Okay, so we talked about doing passive traffic analysis, network traffic analysis, and specifically for DNS traffic. So let me give a very, very, very short background on DNS. So what is DNS? It's a distributed hierarchical database, again, the domain name system. It's basically a key value store, and where the keys are domain names, and the values, well, there are many different types of values, but the most common one is an IP address, right? So why is the DNS important? It's a critical part of the internet overall. It's basically a phone book, right? I mean, like where you take a name and you want to map it to a number. And that's what your browser does. Like, for example, when you type google.com on your browser, what your browser does is first thing it issues a DNS query to find what is the IP address related to google.com so that I can connect to the server and get the web content that will be then displayed in the browser. Okay, so that's basically the idea. Next. Now, general purpose devices are not the only ones that actually perform DNS queries. Again, IoT devices do so as well. For example, if you have an Amazon Echo or some kind of smart speaker at home, when you talk to that speaker, and the speaker detects the keyword Alexa, for example, for Amazon. It will activate, and then as you ask a question, your audio, your voice will be sent to a server somewhere remotely in the Amazon AWS cloud. And now to find that server in the cloud where your audio needs to be sent to be interpreted, right? Well, the device will actually issue first a DNS query. And so you can see immediately that actions in terms of actions related to how you interact to a device can influence network traffic. Moreover, there is idle traffic, meaning that even if you don't do anything with the device periodically contacts these servers on the cloud, the control servers for the IoT ecosystem, to basically ask for updates or check if the internet is still on, reachability, right? Checks and whatnot. Um, and and so there is a lot of DNS traffic that is generated by these devices. So I have a couple of questions here. Sorry, go back one slide. One question is, do IoT devices emit DNS queries? And this is easy to answer, and the answer is absolutely yes. But there is one other question that is less easy to answer, which is, can this signal, right, be used for network-based device fingerprinting, meaning creating models that then we can use for identification of these devices somewhere else? Next. All right, so to study these behaviors, right, of IoT devices, what we did was to first build an IoT lab, a large IoT lab with many, tens of different devices of many different kinds. This was built initially at Georgia Tech, and then we expanded it recently with also a lab at UGA, where we continue to collect traffic to study IoT security issues. Next. Okay, so the previous question that I had was, okay, is there enough signal in the DNS traffic, right, in that we can observe passively at the ISP level, for example, to detect, uh, to distinguish between IoT devices and between IoT devices and non-IoT devices as well. So among IoT devices, but also compared to non-IoT devices. And so in this figure, what you can see, well, so this figure on the right is actually too large to show all, but basically here you can kind of see patterns, right? In this figure, there is a zoom in into a small portion of this figure right here. And let me explain a little bit what this means. So here we have the timeline, right? One entire day of traffic that is being analyzed, DNS traffic. These are the domain names that are being queried by different devices. Every group of here dots basically represent one different device. You can see the name and the models here. These are the specific domain names being queried, for example, and they are represented in sort of like reverse order of the domain labels for. It's a detail, but basically here, what a point represent. Let's say this point. Can you see my mouse? No? Oh, okay. You cannot see it.
It's my mouse.
Oh, okay, that's right. Sorry. So the every dot, what it means is essentially one query to a specific domain. So if you look at let's say the Sonos speaker, and you see all the dots under the msmetrics.ws.sonos.com. I'm reading it in reverse order. Yes, those ones. So those dots represent one DNS query in time, right? So, and as you can see, there is periodicity in many of these behaviors, and you can see that there are patterns, right? Like just visually speaking, there are patterns that you would hope that a machine learning algorithm would pick up essentially. Next. So of course the challenge that we need to keep in mind is that here we are just looking at the traffic of each single device, but when we are looking at the traffic at the ISP level, all the traffic of all of these devices is mixed in, meaning that we will see, because of the NAT functionality is to basically map all the IP addresses from inside the network, which are typically private, into one single public IP address that can be used to communicate with the rest of the internet. then automatically the ISP, which is the service provider that will route the public internet traffic that is coming from your network, will actually see all the traffic that is generated by all the devices in the network as one, almost like one device, right? Because there's one source IP address, and so that's why that can be seen as such. And this poses a lot of challenges from a detection standpoint, because you have all this mixed traffic that actually is coming from potentially many different devices. So this is a challenge that we will need to address. Next. Okay, so now comes the technical part. So hopefully this gives you enough background to understand this part. So we don't have a lot of time to go into all the details, so I will have to be quick. But I will try to do my best to clearly explain at least the approach at a high level. So the modeling approach, which is perhaps the most interesting part for some of you on the ML side. So what are the objectives of these models? First of all, we obviously we want to automatically learn models, right, from the traffic that the IoT traffic generate, build a classifier that will allow us to classify or detect the presence of a specific device in the network. What we want to do, we wanted to do is build one classifier per device, because again, we have this issue of the NATing, where the traffic that is coming from one local network, like a home network or an enterprise network, can actually contain many devices, right? Like a camera and a smart speaker and so on and so forth. And we want to label all of them.
I have a question, Roberto. Is
Sure.
it per device or per device class?
It's per device.
Got it.
Yes, per device, per make model, actually. Yeah. And that was, and I will show later that sometimes this doesn't work well because devices from the same vendor have very similar traffic, and so you cannot distinguish the model, but at least you can identify the vendor and the class of devices as well sometimes. But ideally, we would like to detect, make a model specifically. And we also wanted to choose a method that allows for explainable results, right? So something that you can actually show to an analyst, let's say, if you wanted to, and like a network or a security analyst or an IT person at the very least, and this person would be able to say, oh yeah, I mean, I understand why this device was detected. Uh, and of course, we wanted a model that is very um, computationally efficient in a way, right? So nothing too complex, because as I will talk about later, I mean, we have tens of millions of clients in an ISP network, huge amounts of DNS traffic, well, hundreds of billions of queries per day, maybe even trillions of queries, and so we really need to be fast. Okay, so the approach that we took to try to meet these objectives was essentially an old school approach, but it worked well because of the large scale issue, right, that we had, and the approach is document retrieval, really, right, information retrieval techniques. So here we created an analogy in which each device can be seen as a document, and the terms in the document are actually the domain names that are being queried by the device, right? So you can think of, okay, I'm going to observe the DNS traffic from a device for a certain particular amount of time, let's say 1 day, and all the domains that are queried, I put them in a text document, right? And then I count them. I count their frequency, and then I have a document frequency, I mean term frequency that I can compute. At the same time, if I look in aggregate at all the devices in an ISP network that are querying domain names, well, basically every device is a document. I can also compute the inverse document frequency, which means for every domain name, right? Because every domain name is a term, right? I can compute the inverse frequency of that term across all the possible documents, meaning all possible devices in the ISP network. And then the matching by cosine similarity, right? So which is, again, it's very traditional approach in terms of document retrieval. We are just finding a way to adapt it and map it into this problem of IoT device detection. Next. This gives an overview of the entire system. I will go fast here again because we are kind of running out of time. So basically we just do the traditional supervised learning, right? Where we have the IoT traffic collected from the lab, we extract the term frequencies, and then which means the domain name frequencies, right? And then the IDF part we collect from passive DNS traces collected at the ISP level, right? Domain names that are being queried by all the devices, like we said earlier. And then we have a way to automatically tune the detection threshold on the similarity scores by using both positive and negative ground truth. I will talk a little bit later about how do we collect negative ground truth, which means labeled DNS traffic related to non-IoT devices. Okay, because obviously you need the contrast, right, between what looks like an IoT and what doesn't. So this allows us to basically learn IoT DNS fingerprints with detection thresholds also on the similarity scores. And then, of course, we use these models for matching, right, on never before seen ISP traffic. Next. Okay, so again, I will not go through all the details here, but basically, again, here's we map an IoT device into a document and we compute the term frequency. So the little box that you see on the bottom left is a document. We have a device identified by a unique IP address in the lab, right? And we create the document as all the domains that are being queried by this device in a specific amount of time. And then for each one of these domains, we create the term frequency. We compute the term frequency, how many times in a day this has been computed. There are details related to DNS caching and dealing with it and so on, but I will not be able to go into the details of that. Next. Like I said earlier, we need to compute the inverse document frequency. So we look at DNS traffic at the ISP level, all the client networks, and we compose, we list all the domain names that have been queried by all the devices or all the networks in the ISP, large ISP networks. This means like tens of millions, actually hundreds of millions of devices, right? We consider only domain names that are also queried by IoT devices to eliminate all sorts of noise that is related to domains that are completely generic, that have nothing to do with IoT. And then for each one of these domains, which are terms for us, we compute the inverse document frequency, which is the usual thing that you would do in document retrieval with some tweaks. Next. And then, of course, once we have the ATF ID, so we have, like we saw in the previous slide, the 2 slides previous, the term frequency, right, for the IoT document, right? And then we have the IDF, the inverse document frequency for each term that we saw in the previous slide. And this allows us to, for every device, compute a TF IDF vector, right? So it's for the ones of you who are familiar with information retrieval, this should be quite easy to see. And then what we can do is matching, right? So in the looking at future traffic, right, in the ISP network, what we can do is take network traffic, DNS traffic coming from one specific client network at the ISP level, and compute the TF IDF vector for that traffic. And then, of course, we compute the cosine similarity between that and the IoT device fingerprint, meaning the TF-IDF vector for that device. And then we have a threshold for detection purposes that, like I said earlier, is learned automatically. And if you go to the next slide, I think we can explain why and how. So to compute automatically this detection threshold, we need negative examples, right? So we know how the TF-IDF vector looks like, but we need to match it against things that we know are not IoT devices, right? And then set a threshold automatically so that we minimize the number of false positives while keeping, of course, the matching feasible, right? For the device that we're interested in. There are a lot of details here related to web traffic and how do we leverage web traffic and user agent strings to label non-IoT devices. Very broadly speaking, what we did, or like at a high level, is to leverage the fact that we monitor the Georgia Tech network traffic, and although most of the web traffic nowadays is encrypted, and you wouldn't see this information in clear text, what happens is that there is a little bit of non-encrypted traffic coming out of devices, phones and iPads and whatnot, that allows us to actually extract some, tiny bits of information that are actually critical to identify non-IoT devices. For example, you see these strings Mozilla 5.0 something something something, right? And these leak information about what device is actually generating this traffic, this web traffic that is asking for web pages and whatnot. And although we don't see the content of the web pages, typically, I mean, all of that is encrypted after redirections to, HTTPS and whatnot. But there is a little tiny signal that we can leverage for labeling. And so we were able to label thousands and thousands many tens of thousands actually of devices that are real world devices, like used by users, and so they generate DNS traffic like naturally, right? And these are real world, right? They give us a very solid base to evaluate our system in terms of false positives in this case. And then for the positive ground truth, of course, we have the lab data, IoT lab data that we use. Next. This is more detailed, but just wanted to mention, so we take each, like I said earlier, each device fingerprint as a single classifier. And then we first look at each single classifier independently and how it performs on both non-IoT traffic never seen, of course, during training, non-IoT traffic as well as IoT traffic. Um, and basically here, what this graph is showing on the bottom is the partial AUC with a 1% false positive cutoff, and you see both the average, the blue dots are the average basically results, and the box plots basically show, because we repeated the experiments over many time windows, and so that's why you see a distribution. And yeah, so each device has its own results basically. Next. Okay, so and this is the confusion matrix in terms of looking at how, like, the confusion among devices themselves, right? So if I take one fingerprint and I match it against another different IoT device, will it match or not, right? And here it shows that the diagonal shows that actually this matching is highly accurate, and there is some confusion in some cases where the devices are from the same vendor. And the reason is that they run the same software. They do almost the same thing, but they're slightly different models of the same device. And so that's why we have confusion. Next. There are many other experiments that we performed in the paper, as you can imagine, to test, what if you put all these devices within the same LAN with a NAT, and so all the traffic is mixed in, like we said at the beginning, will we be able to still detect the devices? And the answer is yes for many of them. Just to summarize, I mean, there are many details of the experiments, but um, just to summarize, basically the takeaway is that we were able to detect 40 out of the 52 IoT devices that we had in the lab with no false positives, even if their traffic is completely mixed in among themselves and among any more than 60 non-IoT devices chosen randomly, like iPads, iPhones, and all these are real world devices used by real people. We are just taking their traffic and basically mixing it in with our IoT traffic and doing the detection. And finally, I just wanted to mention that implementing this to do efficient matching was a nightmare. We had to write like Scala code for Apache Spark, large clusters, compute clusters that we used at Georgia Tech. But this allowed us to basically do matching of all the 50 and more IoT device models that we had over more than 40 million client network traffic, traffic from more than 40 million client networks in a very efficient way, like taking one entire day of DNS traffic from the ISP network and matching all the 50 and more IoT fingerprints would take only 70 minutes of compute time on a large cluster because of all the optimization of the code. And next. Yeah, and so that's pretty much all. And I just want to thank my collaborators at Georgia Tech, and we released the data for these related to this work. So all the IoT lab traces that can be used for other purposes, or to replicate some of the results as well. And we are also expanding these data set, like I said earlier, with more devices and with more diverse settings of the same device in multiple with multiple how to put it, deployment geolocations as well, simulated, but in a way that is very realistic. So if anyone is interested in getting access to this data, you can certainly contact me.
I'm interested. I would love
Okay,
to
sure.
have the data.
Yeah,
And
absolutely.
and I'm trying to set up a similar setup, so maybe we can collaborate and use different locations with different
Oh,
types of
absolutely.
devices and see how things change.
Yes, that's a good idea. That's all from me. And if you have any questions, I'll be happy to try to take them and answer it.
Awesome. Thank you so much, Roberto. Let me see. I will stop sharing so that I can also see if there are questions. Uh, I don't see them in chat, but maybe if you just want to ask questions directly. This was excellent. I think you described everything so nicely for somebody who is not in security. I think it was perfectly clear. Thank you so much.
I had to balance. I didn't have a lot of time to go into the details of the data mining, machine learning part. I tried to find a balance though, because yeah, like you said, the audience was mixed. So I hope
Yeah.
it was okay.
Okay, any questions?
So, Roberto, is the data that you're collecting through this IoT Finder, I'm just looking at your website that you've shared, is
Hmm.
that still ongoing on adding heterogeneous devices? I know you said you're trying to look at different geographical settings or
Yes.
scenarios to make it more realistic.
Yes, yes, exactly. So the data collection is still ongoing. So the data, the website. Let me put it this way: the amount of data that we
Mhm.
generate and store from the IoT lab is huge.
Mhm.
Even though the devices are mostly idle. But it's huge, so it's difficult to share it continuously and so on. But if there is a specific interest, right, from a researcher, and they want to contact us, by all means, please reach out, and we'll find a way to share, at least like a window of data that is large enough for you to do experiments, right? But it's
Mhm.
it's easier to share, I guess.
Yeah, yeah, we would be interested in looking at this, more for some of the models that we are building that are inspired by biology and to show some of the robustness. So,
Absolutely.
yeah, we can talk offline. I think there are some students who have questions, Gabriela.
Yeah, I see Jorge was first. So do you want to ask the question directly, Jorge? You're
Yes, hello,
still mute.
Dr. Roberto. Can you guys hear me?
Yes.
Yes.
Yes. Oh, so my question is, can through your IoT finder using the DNS traffic, can you identify um, new devices? Because in your test setup, you know the device beforehand, and
Yes.
you're setting a fingerprint. So in the real world, I would imagine you can't test all the IoT devices to to match the fingerprint. You need to develop some system to estimate that device, or is that information in DNS traffic or maybe some other internet protocol?
Yeah, that's a very good question. So unfortunately, like the short answer is no, meaning that like you have to build the fingerprint of the device before you can match it, obviously. Now, one thing that you could do is, in some cases at least, detect a class of devices, right? So like I showed briefly, I didn't have time to go into the details, but in the confusion matrix, like you sometimes you can at least sort of like build the fingerprint for the vendor, like so that you have at least an idea of you know, what class of, maybe the class of devices as well, not just the vendor, right? Sometimes you can aggregate, and if there is a new device in that class, it's likely that it will share firmware code and does behave potentially similarly, right? In that case, you can do some generalization, but in general, no, you have to build specific fingerprints. Now, this is difficult to do even actively. I mean, passively is more difficult than actively, but if you do active probing, which we have been working on, um, it's also difficult because you have to create a fingerprint anyway. Sometimes you can use some protocols like UPnP. Um, I don't know if you're familiar with it, but basically sometimes you can actually query the device and tell the device, what are you? And the device actually tells you the exact model, the exact vendor, and the serial number, and so on and so forth. But you have to be within reach, right? In the local network and so on. And so this is not always possible, as you can imagine, a large scale. Yeah.
Thank you.
Mhm.
Uh, there is one more person who is interested in the DNS traffic analysis. I
Sure.
don't know if you have a particular question, Vasuda.
Yes, I do. My research area is more like related to the traffic analysis using DNS protocol, morely related to exfiltrating or kind of communication with some CNC. So I was
Okay.
wondering if there is any such evidences in the data you collected.
For exfiltration, not really. I mean, so we looked at the IoT traffic generated by mostly idle devices. Although, I mean, in the lab there is activity, like human activity, you know, and so like smart speaker can pick up or like the activity or like the video cameras and whatnot, right? They can. Um, and respond accordingly, right? But mostly the devices are idle, so the learning really the ML algorithms that you would use are will mostly pick up the idle traffic, and there is no specific labeling in our data in terms of when the device is idle and when not, because it's very difficult to track. But again, it's mostly idle traffic. Um, I mean, the only exfiltration I can think of is just looking at basically, yeah, the video and audio signal that the devices would be sending to the cloud points. I mean, you can think of that somehow as maybe data exfiltration, but no, I mean, we didn't have specifically compromised devices, right? That we compromised and then tried to maybe somehow illegitimately exfiltrate data.
Oh, so can I think of the data collected in the setup as wide variety of DNS benign data?
Yes. Yeah, it's normal data that normal in the sense that it does not originate from illegitimate or illegitimate use or compromised machines.
Okay, so the idea is basically train the models with more benign variety of traffic so that it would pick up some kind of anomaly that deviates from this benign. Correct.
Well, for us, it was purely to identify the same device, right, somewhere else, right, in another network. Uh,
Oh,
you could do, like, if you are interested in doing anomaly detection, right, you could use our data to do that, right, but there you need to be careful because obviously you have to be careful in terms of IoT devices that are used in a different way, may generate somehow different traffic, right? So we focused on the idle traffic, right? Because our devices are mostly idle. But you have to be careful about interaction between users and devices that at different times and so on may generate different traffic. And so if you do a pure anomaly detection, then those can, of course, deviate. I mean, those interactions may cause the traffic traces to deviate from the idle and therefore cause false positives potentially, right?
Yes, yeah. So I think I'm anyways interested in looking at the traffic collected by you, at least some instances, if you can help me with that. I will
Yep.
reach back to you through an email placing a request.
Yeah, absolutely.
Thank you. I would also read the paper to get even better understanding of it. Thank you for the seminar.
Yeah, thank you.
It's helpful. Thanks.
Any other questions? I have a question about the potential of detecting, malicious DNS queries. You said that you haven't done anything to the devices. The devices were perfectly normal. Are you going to extend the work and start leveraging some of the vulnerabilities that we know exist on some of these devices and see how they can manifest themselves?
So we thought about it. The problem is that it's not easy to do in the sense that, um, first of all, we didn't want to break our devices. Sometimes they
True.
can get bricked completely. Uh, uh, but also, it's not that easy to actually find a vulnerability that works specifically for a type of malware that is real world, that actually exists somewhere, right? That can exploit the device and be implanted and so on and so forth. So I think it's doable, but there are challenges. So we haven't looked at that. We have looked at well, there is one student at Georgia Tech who has done work on uh, studying IoT malware, but in a VM environment, right? So like at scale. So like thousands and thousands of malware samples analyzed in a simulated or emulated IoT environment, basically. Yeah.
Nice. Okay.
To expand on that point a little bit, with your fingerprint, right, which is like in your example, is just benign, non-modified IoT devices. Can you find like deviation of like a different DNS or IP query that's out of normality of the device to find a potential um, exploitation or something wrong,
Yeah.
right?
Yeah, so yes, I mean you could the again like I said earlier, I mean I think the main issue is that in general for modeling IoT traffic is that you have to take into account that as users interact with the devices will respond by generating different types of traffic. So what that means ultimately is that if you look at detailed information such as patterns with respect to frequency of certain specific types of traffic, DNS and others, those details will vary, right? I mean, they will not be constant because of the interactions between humans and devices being non-deterministic in a real world setting. And so you have to be careful with that. And so think deeply about how to model the traffic in a way that does not, how to put it, that does not cause too many false positives, right? When you actually deploy it in the real world. Let me add one thing, which is that the traffic that we have from our lab, it does include interaction with human beings. I mean, traffic that is related to responding to human behavior, again, because of, even if we didn't try explicitly, the smart speakers will sometimes activate, pick up whatever language, or cameras, of course, will always pick up, movement and so on and so forth. uh, the good thing is that, if you're careful the way you model the traffic, you would expect that for a malware, the set of IP addresses and domains that are contacted by the malware would be completely outside of the norm, meaning like completely outside of anything that you would see in the normal traces, because they would not contact the cloud endpoint. They would contact a command and control server, for example, and something like that, that obviously you would never see in the normal traffic. So yeah, so again, if you're careful, I think that the data that we collected can still be used for anomaly detection. You just need to be very careful the way you do it so that you don't generate too many false positives.
Okay, I think we can stop there, right? Thank you so much, Roberto. And I will try to connect you to the students who are interested in the data, and if they have more questions. And I will talk to you also, because there are some potential collaborations there. Okay.
Yes, happy
Thank
to
you.
discuss more. All right.
Excellent. Thank you.
Okay. Thank you.
Talk
Take
to you
care.
soon. Bye. Bye.
Bye-bye.